In this lesson, we will learn what a filter cache is, why architects sometimes put it in front of the level 1 data cache, and we will compute the new average hit time and the projected change in CPI when the filter cache captures 40% of level 1 data hits. Here is the high-level picture. A memory access from the core first goes into the tiny filter cache, then, only if it misses there, proceeds to the level 1 data cache. The idea is to answer some frequent accesses faster in the tiny cache and to avoid waking up the larger and slower level 1 structure. The filter cache has a latency of 0.3 nanoseconds, and the level 1 data cache has a latency of 0.6 nanoseconds. The phrase captures 40% of L1D hits means the following. Consider all the accesses that would have been hits in the level 1 data cache. Of those, 40% will now be satisfied immediately by the filter cache, and the remaining 60% will miss in the filter and still be hits in L1D. Graphically, we show a green fast return path for 40% and an orange path that continues into L1D for 60%. Now, let us compute the new average hit time for the hit path. Before the filter cache, the hit time was 0.6 nanoseconds in level 1D. With the filter cache in front, every access first pays 0.3 nanoseconds. Then, with probability 1 minus 0.4, or 60%, we also pay the level 1D latency of 0.6 nanoseconds. So the new average hit time equals 0.3 plus 0.6 times 0.6. That equals 0.66 nanoseconds. Notice that this is a little slower than the original 0.6 nanoseconds because 40% capture is not quite enough to overcome the extra front-end lookup cost for the rest. Let us make this visual. On the left, the old hit time bar is 0.6 nanoseconds long. On the right, the new average hit time bar is 0.66 nanoseconds long. The difference is 0.06 nanoseconds, which is a 10% increase in the hit portion. A neat insight: there is a break-even capture rate where the filter cache does not hurt the average hit time. Set 0.3 plus 0.6 times 1 minus c equal to 0.6 and solve for c. You get c greater than or equal to 0.5. In other words, the filter cache must capture at least 50% of the level 1D hits to avoid slowing the hit path. Now, how does this change in hit time affect CPI? The additional cycles per instruction depend on three things. 1. How many data accesses occur per instruction. 2. The processor clock period. And 3. The change in average hit time. The general formula is delta CPI equals the data access rate per instruction times the new time minus the old time divided by the clock period. Let us plug in one concrete example just to see the scale. Suppose the clock period is 1.0 nanoseconds, which is 1 gigahertz. And suppose on average 0.3 data accesses happen per instruction. Then delta CPI equals 0.3 times 0.06 divided by 1.0, which equals 0.018 cycles per instruction. This is a small slowdown, but real, coming purely from the slightly longer hit path. The exact value in your design will depend on your actual access rate and your clock. To cement the intuition, let us look again at the two hit paths and their weights. 40% of hits take only 0.3 nanoseconds in the filter cache, while 60% take 0.9 nanoseconds, which is 0.3 plus 0.6. The weighted average of these two cases lands exactly at 0.66 nanoseconds. Summary: with a 1 kilobyte, 4-way filter cache of 0.3 nanoseconds placed before an L1D of 0.6 nanoseconds, and capturing 40% of L1D hits, the new average hit time becomes 0.66 nanoseconds. That is a 10% increase over the original hit path. Using the general formula, the projected change in CPI equals the data access rate per instruction multiplied by 0.06 nanoseconds over the clock period. If your design needs a speed up, aim for at least 50% capture, or make the filter look up even faster, or both.